Generally speaking, all the numbered notes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So those notes were written by Dr. Ginsky and I, and they're tailored to this class. So and they are your study guide. There really weren't any topics in those notes that we weren't intending for you to learn in this class. Maybe with a couple of minor exceptions, so that's kind of what I want to point out as we go along. Section 1 was really the basics of languages and automata, and so you should be comfortable with all of that material. Regular expressions, finite automata expressed either as state diagrams or as tables. You should be comfortable going back and forth between all those forms, and in English. Section 2 was introduction to grammars, and this was just the bare bones introduction to grammars. We greatly expanded on this when we talked about BNF and EBNF grammars, and so these basics of context-free grammars in section 2, you should be really strong on all of that material. Section 3 was about lexical scanning, and this is probably an area where a number of you will want to review. You should certainly understand the overview of the compilation process and the various steps and their purpose. And then you should understand what's a token, what's the principle of longest substring, and be able to do examples. I think in your first quiz you had to do a lexical scan, and I didn't require you to identify the types of tokens that resulted from the scan, but you should be able to indicate that if I ask you to do something similar. Let's see here. There's the principle of longest substring. There's an example. One thing, this section in section 3 notes that says extra, that section I won't be on the test. It really is just extra. Then we did BNF, Bacchus-Naur form, and parse trees. And quite a bit of this section didn't make it onto the quiz, into a quiz. So what was in here? Well, what constitutes a BNF grammar? Showing a derivation as a parse tree. Again, terminals and tokens. I'm sorry, terminals, which are the same as tokens, and non-terminals. And then we saw 2 different sources of ambiguity in grammars. We saw ambiguity due to left to right associativity, and ambiguity because of operator precedence. And so we saw examples of those and how to make corrections in the grammar so that they did no longer have those ambiguities. So I don't think any of that made it into the quiz that we had, your second quiz. So you probably are going to want to review that. Then we did EBNF. And so for EBNF, you should be know that pretty well. You had that in a homework. Converting between BNF and EBNF, you probably had something like that on a quiz, but you'll want to review that. You should know all the new meta symbols for EBNF, and how to properly draw syntax diagrams for an EBNF grammar. And then there was this table at the end showing the standard ways of notating particular elements of grammars in BNF, EBNF, and syntax diagrams. You should be able to apply those correctly. If it helps you to put that table in your notes, that might be worthwhile. chapter here on recursive descent parsing, and of course you had a homework in that, so you're all experts in that. Those questions will be easy. So one thing I won't do, I won't require you to write, I may require you to, given some small grammar, write the recursive descent parser for it. I won't say you have to write it in Java or a particular language. If I ask you to write a parser, I would accept Java, but I would also accept just pseudocode. All the examples in the notes are in pseudocode. So you should know what's the token pointer, what does match do, and how to use those. You had a much bigger example in your homework, but there's also a smaller example here. You should know the issues related to the end of token stream mark. You should also know how to prove whether or not a grammar can be parsed with recursive descent. So you should know the first and second rule of predictive parsing that are described here. This first, the two cases that you have to be able to handle in such a proof. We've been doing a proof off the syntax diagrams, and so if I were to ask you to do a proof like that, it would be off the syntax diagrams. So there was an example here. So that also means you need to understand how to generate first and follow sets. So you're likely to need them in such a proof. So there's some examples in your notes. There's also several examples in the posted solutions for homework 1. Then we had a section on NFAs, non-deterministic finite automata. So you should be comfortable working with either deterministic finite automata or non-deterministic finite automata. You should, of course, know the difference between the two. Of course, when I say the difference, I mean the notation difference, because their expressive power is the same. You should also, in addition to being able to work with them, you should know how to convert from an NFA to a DFA. If I remember right, there was a question on the quiz like that, so and we had a day of practice at it, so you may want to review that, of course. There's plenty of examples to review, to practice. There was posted notes on the Chomsky hierarchy. They weren't my notes, and really the only part on here that I expect you to absolutely know is the actual hierarchy. These days I'm going to go here and change the color, light gray to something like white, and easier, maybe yellow, something easier to see. So you should understand, you should know the categories of languages in the Chomsky hierarchy, and for each of the machines or mechanisms that we have learned, you should know how they fit in this hierarchy. As well as the types of languages. All the other detailed materials in this set of notes I won't be asking you about. We spent quite a bit of time on functional paradigm and the scheme programming language. We've had a homework. You're welcome to put some examples of scheme on your page of notes to jog your memory about how to write code in scheme. I think I should be able to ask you to